Alright, let's start a new sequence of videos here. In this collection of 3 videos, we're going to introduce integral domains and fields. And this is for use either at the end of Abstract Algebra 1 or as a review in an Abstract Algebra 2 class. So we'll start again with just the definition of an integral domain, but actually before we get there, I'm going to have to define one other thing. So the first thing I'd like to define is what's called a zero divisor of a ring R. So a zero divisor of a ring R is a non-zero element, A, for which there exists a non-zero element, B, so that when I take the product of these two elements, I get 0. As an example of a zero divisor, if we're to work in the ring Z mod 6, then the numbers 2, 3, and 4 are examples of zero divisors. None of them is 0. And yet I can take 2 and 3 and multiply them together and get 6, which is 0 in the ring. And similarly, 4 times 3 is 12, which is 0 in the ring Z mod 6. What an integral domain is it's a ring. We're going to require that the ring be commutative. We're also going to require that the ring have a unity. And we're going to require that the ring has no zero divisors. And if you have a ring that satisfies these 3 additional properties, commutative, with unity, no zero divisors, then we call that ring an integral domain. Just as a little bit of a side note here, integral domains were really defined as the next step closer to capturing the properties of the integers. As we saw in the last sequence of videos, the introduction to ring videos, the integers are an example of a ring, but they behave a lot nicer than some other rings that we have out there. And an integral domain is going to attempt to capture those additional nice properties that are held onto by the integers. So this gives way to our first example of an integral domain. The integers are in fact an integral domain. However, when we now work and we switch from the integers to the integers mod n, the integers mod n are going to form an integral domain if and only if n is prime, which is something that you should convince yourself of. Haven't assigned it as an official exercise, but it's a good thing to work through on your own. Another non-example here, so the previous one, the integers mod n, could or could not be an example, but non-examples are also helpful in the study of a particular object. But the even integers, which we saw in the last set of videos was a ring, fails to be an integral domain. Although it is commutative and it lacks zero divisors, it also lacks a unity. And in our definition, we're going to require that an integral domain have a unity. I should note that this is the way that Gaussian does it, and this is the convention I will follow. I will require my domains to have a unity. But if you do look on the internet and look in other textbooks, that's not always a requirement of an integral domain. The set of n by n matrices with entries in F, where F is either the integers mod n, rationals, reals, or complex numbers, is not an integral domain, similarly, because the multiplication operation in general is not commutative. So matrix rings, which are really great examples of rings for the fact that they're non-commutative, are enough to disqualify them from being domains, so we're going to have to look into different types of rings for our interesting examples of things that are integral domains. Another type of ring we studied was polynomial rings, or rings using this adjoint notation. So if we're looking at f adjoint x, again where f is one of the integers, the rational numbers, reals, or the complex numbers, that will be an integral domain. And notice that I have left z mod n off of this list of possibilities for f, because if we put that z mod n there and we don't put that specification that n is prime in there, then we're not going to have an example of an integral domain when we look at this polynomial ring. And perhaps the next example, which is a good example, a little bit more out of the box, is that the Gaussian integers, z adjoint I, this is another example of an integral domain, and it's a good example because it's a less familiar and less comfortable example for us. Now let's take a minute and let's study the properties of integral domains. Although we have in our definition required that an integral domain have a unity. So that's the third of the 4 group properties. We now require that our multiplication operation is associative, closed, and has an identity. We are not requiring that all non-zero elements be units. And so we are still allowed within an integral domain to have elements with no multiplicative inverse, which is good if we're trying to capture the properties of the integers. The integers have many elements that lack a multiplicative inverse, almost all of them, as we've seen. However, even just adding these 3 requirements, that we have a commutative ring, that we have a unity, and that we have gotten rid of those 0 divisors, we now have that integral domains are going to have a lot of those nice properties that we desire. So in the previous series of videos, we had this sort of rings behaving badly section, where these nice things that we knew and loved about the integers didn't hold in general for rings. What we're going to see is that these properties do actually hold when we move from a ring to an integral domain. So as an example of this, we have the following lemma. If D is an integral domain and A is a non-zero element of D, then AB equal to AC implies that B equals C. And here I'd actually like to do the proof, fairly short proof, but I also want to give a little bit of a warning with this proof. So the first thing we'll do is we'll suppose that AB is equal to AC. It's a little bit tempting to, when you see that equation, AB equals AC, what you are tempted to do is to maybe cancel the A's or say let's divide both sides by A, which division in an abstract algebra class means multiply both sides by the multiplicative inverse of A. However, we're not really allowed to do that because we are not requiring that non-zero elements be units here. However, we still are able to obtain this cancellation result that we'd like. So instead of multiplying both sides by a multiplicative inverse of A, which doesn't need to exist, what we're going to do is add the additive inverse of AC to both sides so that we end up with the equation AB minus AC is equal to 0. The next thing we want to do is we want to use the distributive property in reverse. So what we want to do is we want to factor that A out of this equation. So we have AB minus AC, and by the distributive property that's equal to A times B minus C. And so what we have is that A times the quantity B minus C is equal to 0. Since D is an integral domain, so here we're using the hypothesis that we have an integral domain, this means we don't have any 0 divisors. Because we are lacking 0 divisors, and we've taken the product of 2 elements and gotten 0, one or the other of those elements must be 0. That is, either A is 0, or the quantity B minus C is 0. By hypothesis, we're assuming that A is not equal to 0, so it must be the latter situation, and we must have that B minus C is 0, or alternatively, B is equal to C. Let's do one more property of integral domains here. So let's get another way in which integral domains behave nicely. One of the properties that failed in general for rings is that we saw linear equations could have more than one solution in rings. Let's prove that if D is an integral domain, and A is a non-zero element of that integral domain, then the equation AX is equal to B has at most one solution. So the way that we're going to go about this proof is as follows. So let's suppose that we have 2 solutions to the equation AX is equal to B. So let's assume that Y and Z are 2 different possibilities for X that make the equation AX equal to B true. And what we're going to do is we're going to show that Y and Z are actually the same. So since Y and Z are solutions to this equation, we know that AY is equal to B and AZ is equal to B. By then using this substitution, B is AY and B is also AZ, we can obtain the equation AZ is equal to AY. Now we've just established on the previous slide that we're allowed to cancel. Right? A is a non-zero element by hypothesis of our lemma, so we're allowed to cancel it away since we're working in an integral domain. And this allows us to conclude that Y is equal to Z, and therefore the equation AX equals B has at most one solution. We started with 2, and we showed that they had to be the same. Now as an exercise that I'd like everybody to try, I'd like to take this up one level. We're also used to, in integers, having a quadratic solution, and we're all very familiar with that quadratic formula showing that there are either 0, 1, or 2 solutions to any quadratic equation. And so that's what I'd like us to prove without the hypothesis that we're working in the integers, just with the hypothesis that we're working in an integral domain. So the exercise is, if D is an integral domain and A is a non-zero element of that integral domain, then the equation ax squared plus bx is equal to c has at most 2 solutions. So that's something that I hope you can work through as an exercise. Something I don't necessarily expect you to work through as an exercise, but which is a nice thing to do if you're looking for a challenge and you're looking to take this, to its full depth. This would be to show that if D is an integral domain and A is a non-zero element of D, then the equation ax to the n plus a1 x to the n minus 1 and so on and so forth up through a sub n minus 1 times x is equal to a naught, show that that has at most n solutions. So a polynomial of degree n in an integral domain has at most n solutions. Again, this is an advanced exercise, not necessarily something I expect you to do, but something that's a nice challenge if you're looking for that.